In the last video, we learned how to take the derivative of functions using this method of related rates. And I don't know, I find it kind of fun. Maybe you do, maybe you don't. It's just like the same derivative rules we've been using. We just have to treat different letters differently depending on whether that letter represents a variable or that letter represents a function. To make sure this makes sense, I want to do that exact same stuff in the context of an example. So suppose, for example, that quantity was a function of price. Yeah, that makes perfect sense. The amount you're going to sell is based on what you charge for it. Keeping the numbers a little bit smaller this time. Q of p is equal to negative p squared plus 12, a graph that loosely speaking looks like this. Price is on our x-axis, quantity is on our y-axis, and since we're not interested in charging negative prices, we're really only thinking about this half of this reflected parabola. And you're like, all right, that's all the same as it's always been. Yeah, except now p is no longer just a variable. P itself is a function. It's a function of time. So the quantity that you're going to sell is a function of the price that you're going to charge, but the price that you're going to charge changes over time. And it's given by this formula right here. What if somebody asked you, at what rate is the quantity that you're going to sell changing after 4 weeks? This is a really challenging question, and the reason why is because we're asking at what rate the quantity is changing. So maybe you're thinking like Q prime, but Q prime of what? Well, 4 weeks. So you might be thinking Q prime of 4, but no, this is T that's equal to 4. Q is a function of price, not of time. So we kind of want to know Q prime when T equals 4. Well, we got options. One option is we could come up with quantity as a function of time. Given to us as quantity as a function of price. But if we could make it quantity as a function of time, then we could just take the derivative and plug in t equals 4. The problem with doing it that way is we'd have to compose together these functions. Instead of writing negative p squared plus 12, what we would write is negative something squared plus 12, where that something is p, which is the natural log of t plus 4 over 8 plus 40 over t plus 4. All of a sudden, our function is a disaster. I mean, it's nice that we have quantity written in terms of time. That's cool. So now in theory, we could find q prime of t, and then we could find q prime of 4, and we'd be done. But doing that will involve taking the derivative of this thing. You could compose these functions together and differentiate, like I'm kind of laying out over here, but it might be kind of ugly to do so. Maybe there's an easier way. Maybe we could use related rates. We'd get the same answer either way, but if we use related rates, I think the calculus won't be as intimidating. How would we use related rates? Well, we'd want to know the derivative of this function q, but now p is a function, not a variable. If you really want to be careful with your notation, we're figuring out the derivative where t is the variable of negative p squared plus 12. The derivative of negative p squared, I leave the negative alone because it's a -1 coefficient. I bring the 2 down in front using the power rule, leaving the p completely alone and raise it to the first power. But then I'm not done. I have to multiply that by the derivative of p, which is not equal to 1 because my variable is t. So the derivative is p prime. I then have to add to that the derivative of the 12. 12 is just a constant, so it's equal to 0. What I'm saying is the derivative of negative p squared plus 12 with respect to the variable t is equal to negative 2p p prime. If you want to write these more in function notation, it's negative 2p of t times p prime of t. Q prime of t, I now have an expression for the derivative of quantity with respect to time. That's the important thing here. So if I want to know q prime of 4, the same thing I'm looking for over here, all I have to do is change all the t's in this expression into 4's. I get negative 2 times p of 4 times p prime of 4. What is p of 4? What is p prime of 4? Well, I could figure those out if I have an equation for p of t. I do, it's written up here. P of t is equal to the natural log of t plus 4 over 8 plus 40 over t plus 4. If I need to know what p of 4 is equal to, I copy this exact expression, changing all the t's into 4's. It's the natural log of 4 plus 4 over 8, 8 over 8. It's the natural log of 1 plus 40 divided by 4 plus 4. 4 plus 4 is 8. The natural log of 1 is equal to 0, and 40 over 8 is equal to 5. P of 4 is just equal to 5. Therefore, Q prime of 4 is equal to negative 2 times 5 times whatever P prime of 4 is equal to. How do I figure out P prime of 4? Well, I have P of t, so I can figure out P prime of t. Take the derivative of this. I'm going to have to use some chain rule here. The derivative of the natural log of t plus 4 over 8 is 1 divided by t plus 4 over 8 times the derivative of t plus 4 over 8. And then I have to add to that the derivative of 40 over t plus 4. Well, 1 over a fraction means take the reciprocal of the denominator. I got 8 over t plus 4 if I clean up this a little bit. The derivative of t plus 4 over 8, think about this as 1/8 times t plus 4. So you can bring that 1/8 down in front and then take the derivative of t plus 4. The derivative of t plus 4 is the derivative of t, which is 1, plus the derivative of 4, which is 0. And then to that, I want to add the derivative with respect to t, that's an ugly looking t down there, of 40 over t plus 4. Well, again, if we think about this a little bit differently, it's easier to take the derivative. Think about this as 40 times 1 over t plus 4. I can bring the 40 out in front of the derivative symbol, and then 1 over t plus 4, I can think of as t plus 4 to the negative 1 power. If I clean up as I go, 1 plus 0 is just 1, and 1 times 1/8 is just 1/8, and this 1/8 and this 8 cancel out, so I get 1 over t plus 4 from my first term, and from my second term, I got this 40 times this derivative. Using my chain rule, I bring the negative 1 out in front, leave the t plus 4 completely alone, and then subtract 1 from that exponent to make it negative 2. And then I multiply that by the derivative of t plus 4. The derivative of t is 1. The derivative of 4 is 0. P prime of t is equal to 1 over t plus 4 plus this negative number, because a positive times a negative is a negative. So instead of writing plus and negative, I'm going to write minus 40 times t plus 4 to the negative 2, which is the same as 40 over t plus 4 squared. Now that I know P prime of t, I can figure out P prime of 4 by copying exactly what I see here, changing all the t's into 4's. I got 1 over 4 plus 4, which is 8, minus 40 over 4 plus 4, which is 8, squared. 8 squared is 64. If I want a common denominator, I'll multiply the top and the bottom by 8 and get 8 64ths minus 40 64ths. I'll get negative 32 over 64, which is just negative 1/2. P prime of 4 is negative 1/2. Q prime of 4 is negative 2 times P of 4 times P prime of 4, which is negative 2 times 5 times negative 1/2. Negative 2 times 5 times negative 1/2 gives me 5. What that's saying is that if quantity is a function of price and price is a function of time, then the rate at which quantity is changing when time is equal to 4 is 5. That's pretty intense. You might argue that it would have been easier to just compose the functions together and take the derivative more directly. And you're not wrong. I think that would have been easier in this specific case. Let's see if we can do it real quick. This negative is a constant. I'll leave it out in front. I'm going to use my chain rule here. The outermost layer is this 2. So I bring the 2 down in front, leaving all this stuff alone. Natural log of t plus 4 over 8 plus 40 over t plus 4. Subtract 1 from this exponent, I get a 1. But then I'm not done. I have to multiply that by the derivative of all that inside stuff, the natural log of t plus 4 over 8 plus 40 over t plus 4. And then I add to that the derivative of this 12, which fortunately is just equal to 0. And here, if you're kind of clever, you might notice that what we have left to take the derivative of is the natural log of t plus 4 over 8 plus 40 over t plus 4, which is exactly p of t over here, which is exactly what we took the derivative of over here. So what goes inside these parentheses is this expression. So we could rewrite q prime of t as negative 2 times this mess times this mess. Holy cow, that's getting crazy. And then I could change all the t's into 4's, and I'd get the same answer that I have down here. Maybe that's not easier. I don't know. Maybe this is just super hard. But regardless of which of these methods you think is easier, I want to make the comment that sometimes you can't use this top method. Even if you have the ability to compose together these functions and take crazy hard derivatives, you might need to use related rates. An example where you'd need to use the related rates method is down here. If you don't explicitly know a function for the price, you just know that the price in 4 weeks will be $5, but will be decreasing at a rate of 50 cents per week. We're still assuming that quantity as a function of price is equal to negative p squared plus 12. We have the same demand function that we had up here, but now we don't know the function p of t. We no longer know that p of t is the natural log of t plus 4 over 8 plus 40 over t plus 4. We're not given that information. What are we given instead? We're told that the price in 4 weeks will be $5. In other words, p of 4 is equal to 5. And we're also told that the rate at which the price is changing, so you're thinking derivatives, will be decreasing at a rate of 50 cents per week at that time. So p prime of 4 is equal to negative, because it's decreasing, 50 cents, or 0.5. We don't know p of t, but we know p of 4 and p prime of 4. We have our demand function over here, and we want to know the change in quantity, so you're thinking q prime, when the time is equal to 4. Well, I can figure out q prime by taking the derivative over here. Just remember that you're taking the derivative with respect to t. So p is a function and not a variable. So the derivative is negative 2p to the first power times p prime using related rates, plus the derivative of 12, which is still just 0. Q prime is equal to negative 2p times p prime. If you want to write this with variables, we could say q prime of t is equal to negative 2p of t times p prime of t. So if I want to know q prime of 4, the rate at which quantity will be changing in 4 weeks, it's negative 2p of 4 times p prime of 4. Fortunately, we know p of 4 and p prime of 4. That's what was given to us up here. So my answer would be negative 2 times 5 times negative 0.5. Negative times a negative is a positive. 2 times 1/2 is just 1. So I get positive 5, the same answer that I got up here. This second example is a little bit more common with related rates. Often you don't know the underlying function, p in this case. You just know that p is a function and you're told some information about it, maybe p of 4 and p prime of 4. And with that information and the ability to take derivatives using related rates, you can get answers like this. Mercifully, that's the end of chapter 2. That's all we're ever going to do on derivatives. We're now going to move into a whole different chapter of our book and a whole different chapter of our class.